This generated visualization represents the continuous, chaotic stream of conflicting data an operating system must manage every second. To keep a machine running, a processor must isolate those incoming tasks, prioritize them, and organize them into a strict, linear timeline. We represent this scheduling problem with three specific variables. We have a set of independent jobs, we have strict time deadlines dictating when each job must be finished, and we have specific profit values, representing the priority or payoff of completing a given task. The objective of a greedy algorithm in this environment is to make immediate, localized choices that yield the maximum total absolute profit without violating a single time constraint. To understand exactly how this is achieved, we will manually execute a dry run of the CPU's logic. Then, we will calculate the mathematical time complexity of that logic and finally use a formal exchange argument to prove why this strategy consistently produces an optimal result. Mastering the code is the first step. Understanding the mathematical proof behind its efficiency provides the insight needed to apply these principles to larger, more complex systems. This animated data table holds our raw input, 5 unorganized jobs labeled A through E. Each has a specific deadline and a designated profit value. The algorithm's very first step is to prioritize the highest value items. It completely ignores the deadlines and sorts the entire dataset in descending order based strictly on the profit column. Next, the system scans the deadline column to locate the absolute maximum deadline value. Here, the highest deadline is 3, so the algorithm provisions 3 empty time slots to form our schedule. Now the execution loop begins. The algorithm selects the most profitable task, Job A. Job A has a deadline of 2. The system checks slot 2, finds it empty, and places Job A exactly at its maximum allowable deadline. The second loop targets Job C, which also has a deadline of 2. The system checks slot 2. It is occupied. The algorithm must now search backward. It checks slot 1, finds it empty, and drops Job C into the earlier space. Job D triggers the rejection condition. It has a deadline of 1. It targets slot 1, but slot 1 is already occupied by Job C. Because there are 0 available slots earlier in the timeline, it fails. The algorithm rejects Job D. Job B has a deadline of 1 and faces the exact same rejection fate due to the lack of early slots. Finally, Job E enters the loop. It targets its deadline at slot 3. The slot is completely empty, so it drops in successfully without requiring any backward search. The algorithm finishes by summing the accumulated profit from our 3 successfully scheduled jobs. 27, 100, and 15 yields a maximized output of 142. This mechanical, backward-searching loop solved our microdata set. However, the repetitive process of checking each slot backward creates a significant computational cost as the input size increases. This diagram breaks the algorithm's time complexity into 2 distinct phases. Phase 1 is the initial sorting of the dataset. Using an efficient sorting method, this requires O of n log n time. Phase 2 is the slot allocation. Let n represent the total number of jobs, and m represent the maximum number of time slots available. The worst-case scenario occurs when every one of the n jobs has a high deadline, and the system is forced to search backward through all m slots for every single job. Typically, the maximum deadline is proportional to the number of jobs. Replacing m with n results in an expression of n multiplied by n, yielding a quadratic time cost of O of n squared. When we combine the 2 phases, the quadratic cost of the allocation phase dominates the log linear sorting cost. The overall time complexity of the basic algorithm is O of n squared. Utilizing a disjoint set data structure can optimize this. By eliminating the backward search, the allocation time drops, bringing the total overall time complexity back to O of n log n. For space complexity, the algorithm requires memory to store the job list and the time slot array. Since these scale linearly with the input data, the space complexity is O of n. This analysis highlights a critical engineering reality. Even a logically correct algorithm can become impractical if its time complexity prevents it from scaling to meet real-world demands. This split-screen comparison illustrates the risk in scheduling, attempting to secure a high-profit job by doing it as early as possible. Placing a task early removes a slot that might be needed by more urgent tasks. As you can see on the right, latest slot allocation preserves future flexibility without losing any of the profit. To prove mathematically why this greedy choice always yields the maximum possible profit, computer scientists use a method called the exchange argument. Consider this timeline. Suppose there is a perfect optimal schedule that achieved maximum profit without using our greedy choices. It contains a lower profit job in a slot where our algorithm would have placed a higher profit job. The core of the proof forces a swap. We take the optimal schedule's lower profit job and we replace it with our algorithm's highest profit choice. Because our greedy job is inserted into a valid slot before its deadline, the schedule remains valid. In this new schedule, we removed a low-value item and swapped in a higher-value item. The new total sum must increase, or at the very least, remain the same. If we repeat this swap for every decision in the schedule, the hypothetical schedule eventually transforms into our exact greedy schedule, without the total value ever decreasing. The exchange argument confirms the strategy. Prioritizing immediate high value and delaying execution to the latest possible slot ensures that no potential profit is left on the table. This specific implementation relies on a rigid constraint. It requires that every task takes exactly 1 unit of time to complete. If jobs require variable execution times, or if you introduce multiple processors to the environment, this specific greedy logic will not produce an optimal result. For university Viva exams, you can recall the mechanics of this algorithm using this memory aid. SHLM. Sort the dataset, isolate the highest profit, allocate it to the latest slot, yield maximum profit. This finalizes the mechanics of job sequencing with deadlines. In the next module, we will apply these greedy principles beyond simple linear lists. We will move into interconnected networks to build minimum spanning trees using Prim's and Kruskal's algorithms.